So in this video, we're going to discuss a little about what a limit of an ordered pair actually means and do a few examples. So first, let's review what a normal limit is. Okay, let's review what a normal limit is. So limit, if you have limit x tends to a for f of x equals L. This means that if x gets arbitrarily close to a, then f of x gets very close to L, right? And so the limit of an ordered pair is really very similar. So if we have limit, first we have to know what a function of an ordered pair looks like, right? With the domain as an ordered pair. So if you have f of xy, right, then this basically means that the domain, or you can view it as the input, is an ordered pair, and the range is a real number. And you can also plot this on a three-dimensional coordinate system by taking z equals f of xy, right? Okay, so now we have that out of the way. Let's proceed to what this kind of limit looks like. So if you have limit f of xy as xy tends to ab equals L, that means that as x approaches a, as x gets very close to a, and as y gets very close to b, you're going to have this whole function f of xy getting very close to L, right? So now let's look at a more formal definition of the limit, right? Basically states that if you have, so let's take this itself. Let's take this expression here, and this equals L. The limit equals L if for every number epsilon, greater than 0, and delta greater than 0, and xy belongs to the domain of the function, then it exists only if 0 is lesser than root of x minus a whole square plus y minus b whole square is lesser than delta. I'll tell you how we get that in a minute. It's lesser than delta, then mod of f of xy minus L is lesser than epsilon, right? Okay, so now what does this mean? I mean, how do we get the weird expression that root x minus a whole square and root y minus b whole square? Well, a graphical aid might help you. So, so let's go to this beginning. And okay, so here we have a Cartesian system, a Cartesian coordinates, and here we have the point AB. Okay, and then what we consider is something called a circular neighborhood, right? A circular neighborhood is basically all the points in this circle around AB. Okay, and we consider, while taking the limit, we're basically saying that if the limit exists, then for all these points in the circle, we can make the circle arbitrarily small, right? So for all points in this circle, right, there must be a number corresponding. If we have this, if L is the limit, then we have this as L plus epsilon. Okay, L plus epsilon. Here is L, and L minus epsilon. For every point in this circle, there is a number between L plus epsilon and L minus epsilon. So that's that's how you get that x minus a whole square and y minus b whole square. Because if you remember, that simply represents the radius of the circle, right, from the Pythagoras theorem. That simply represents the radius of a circle. Right? And what you're saying is that the point must be within the circle. That's how we get that expression. Right? So let's do some examples now. Of course, you also remember something. I hope you remember something about what left-hand limits are and what right-hand limits are, right? So so how do we define a left-hand limit? Well, if you have this thing again, and maybe have some function like that, and this is a, say, so a left-hand limit is when you approach a from, well, the left-hand side, right? So in the left-hand limit, all your values are lesser than a as you're approaching the limit, right? And for the right-hand limit, it's the opposite, right? All your values are greater than a, and we only say that a limit exists if the left-hand limit equals the right-hand limit. And for limits of an ordered pair, it's kind of the same thing, right? So of course we don't have a left hand and a right hand thing for 2D stuff, right? We don't have we can't define a left and right for this. Instead, there are infinitely many number of ways to approach this limit. For example, I could approach it from this direction. I could approach it like this from squiggly line. I could do a lot of stuff. So let's take a look at one example. So let's say we have limit x, y approaches 0, 0, 0, 0 of x square minus y square divided by x squared plus y squared. Right? Now let's approach it along the x-axis. So what we have here, we have 0, 0 right there. And if we approach it along the x-axis, like this, then our y-coordinate is going to be 0, right? So we can just plug in y0 there. So then what do we get? We get x squared by x squared, that equals 1. Right? Now let's approach the same limit along the y-axis. Okay? And if we do that, you see that the x value takes 0. So then we have minus y squared by y squared, which equals minus 1. Now you see, obviously 1 does not equal minus 1. So what we conclude from this expression is that this limit does not exist. Right? This limit does not exist because for the limit to exist, no matter in which direction you approach the limit, it should be the same thing, right? And we'll just do another example. Let's take limit of x y square divided by x squared plus y squared. and this xy approaches 0, 0, 0, 0, 0. Right, now what is this? So let's first try approaching it along the x-axis. That means y 0, right? So that just becomes 0 by x squared. That's simply 0, right? So now what if we approach it along the y-axis? So then x is 0. So if x is 0, you get the same answer, 0. But let's try approaching it along the parabola, right? Along the parabola x equals y squared, and see what we get. If x equals y squared, then we get hold on. If x equals y squared, we get, let me just adjust this thing. That's y to the fourth divided by what's that? Y to the fourth plus y square. Sorry, 1 minute. Sorry, I just messed that up. If we take x equals y squared, then that becomes that becomes y to the fourth. Sorry, this was y to the fourth. Yeah, then it makes sense. So that becomes y to the fourth divided by y to the fourth plus y to the fourth, and that equals half. So you see, although we got 0 from both the directions, we approached it along the parabola, and we get half, which is kind of weird, and that just says that this limit does not exist. So I find this pretty fascinating. I mean, there is really no way, I mean, there might be, but there's no way I'm aware of that you can actually definitively say that the expression does not have a limit. You know, I mean, there are infinitely many directions. I mean, we could have even taken a cubic, you know, approached it along the cubic, and to see what happens. But if you have any, if you know any method that we can use to know if the limit exists, then please write it in the comments. And hope you enjoyed the video.